Last time we talked about contextuality using triangles. Today I want to talk about edge coordinates, which are a mathematical tool that we can use to represent distributions on triangles. The basic idea is that when I have a distribution, I have a collection of numbers inside of this triangle, and I want these to be normalized. What normalization does is it imposes a constraint, and that constraint means that it reduces the dimensionality of the space that we're in. So if you remember in the first or second lecture, what we had is that if you have three possible outcomes, then in principle you have three axes, but then normalization requires you to be on a two-dimensional subspace of that, like this. And that's exactly what happens here as well. So the basic idea of edge coordinates is that we're going to be able to represent any collection of four numbers that are inside this triangle just by using the distributions that are on the edges. And now you may say to me, okay, but listen, each of these distributions here are two numbers, but again, these are also normalized so that px0 plus px1 equals 1. So without loss of generality, we can actually just talk about representing any of these four numbers in here using just the zero component, py0 and px plus y0. And we'll see how that works in just a moment. So the claim, just to be more specific, is that all distributions inside the triangle, p, x, y, a, b, can be expressed uniquely by the marginal distributions as so. And as I said, we can just treat these zero components. It's a little bit nicer to just, it's for convenience, but there's nothing that requires us to choose the zero instead of the one. So here is the proof of this statement. So for simplicity, let's just write this. This is supposed to be xy. The xy component, just write this as PAB so that we don't have to write the xy's all the time. And then we also have these three facts, which are just coming from these marginals here, which is that the zero components are given as follows. Px0 is p00 plus p01, py0 is p00 plus 10, px plus y0 is p00 plus p11. So let's just try this. What if I sum these three numbers together? What do I get? If I sum these three numbers together, then I get, for each one, I have p00 appearing once. So I get three copies of p00 and then the remaining ones. I split off one copy of these so that I have the numbers that are inside this bracket and then two p00s left over. But of course, because of normalization, I have that this all equals to 1. So rearranging, I have 2p00 plus 1, and it equals to this side over here. Rearranging, I have this formula. Now I want to solve for p00, and when I do that, I get that p00 is 1/2 times the sum of these numbers minus 1. And similarly, we can write the rest of the terms just like this in terms of these marginals. Let's see how to do this for one other example. And as an exercise, you guys can finish the proof. So, and the other steps are very analogous. So it's not leaving much to the imagination. So imagine that we look at px0, which is p00 plus p01. Now we want to express p01 in terms of the marginal distributions px0. But of course, p00 through this formula is already expressed in terms of the marginals. So all I need to do is write p01 as equal to px0 minus p00, plug in what this p00 is, and you see that I have that because I'm subtracting here, the 1 becomes positive, these become negative, and this is 1 times px0 minus 1/2 of it, so this stays positive right here. And so this is the expression for p01. As I said, the other expressions follow similarly, and we have this pattern here. We have p00 means that I get a +1, +1, and then a plus, and then -1. And then when this is 0, and then this should be 0, 1, my apologies, 1, 0, and 1, 1. So when this is 0, 1, then I get a plus sign for Alice, a minus sign for Bob. And when this is 1, 0, I get a minus sign for Alice, a plus sign for Bob. And when it's 1, 1, I get that. And in fact, I will make this a little bit more clear. So 0, 1, 1, 0, 1, 1. And when you look at it this way, you see that every time there's a 0, you get a plus for Alice or Bob. Anytime there's a 1, there's a minus for Alice or Bob. And then the other signs are kind of more complicated to understand, but it comes from the fact that you have that 0 plus 1 modulo 2 is 1, 1 plus 0 modulo 2 is 1, so you get the minus sign, and then 1 plus 1 modulo 2 is 0, and 0 corresponds to a plus sign. So it's easy enough to understand these parts. And then you also get these minus 1 plus 1s. In fact, you can compress this, this expression down into just one expression. PAB is equal to 1/2 PXA plus PYB minus this. So as an extra bit of unassigned homework, you guys can try to show that these 4 equations emerge precisely from this expression right here, which is a little bit more compact. So the basic idea is that you have these probability coordinates, and you can get to the edge coordinates by marginalizing. And then you get these coordinates that are on the edges. So I want to use a convention where if I'm just talking about the edges, this triangle is not filled in some sense. So I'm just looking at the edges. So when it's filled in, I use the blue background. When it's not filled in and I'm just talking about the edges, I have no background at all. And the way that but I can always go from these edges to these probabilities by using precisely this formula. So let's see an example of how this works. Say I give you a set of edges with probabilities P1, 0, 0. Then using this formula, and in this case, it's kind of simple to see. We want Alice's outcome of 0 to be 100%. So I have to have something. I have to have that the sum of these two numbers is 1, but then the sum of these two numbers must be 0, and the sum of these two numbers must be also 0. So you get this one. But let's try one that's a little bit less straightforward. So you can show, for example, that if I pick 1/2, 1/2, and 1, and I use this formula, then I can complete this out to be the distribution with, and you can see this. The fact that this is equal to 1 means that I have all of my probability on these two numbers, so that these must be 0. But then the fact that this is equal to 1/2 means that this must be 1/2. And the fact that this is 1/2 means that this should be 1/2. And that fixes precisely what these numbers need to be. Now, the danger with the edge coordinates is that you can have some things that, well, it seems too good to be true, but you still have to impose a couple of things. Remember that you have a minus sign here. You have minus signs. So you can't just pick any old values of these p's, because if you pick one for given other values that are positive, if you pick one that's sufficiently negative, then this whole thing could be negative. So for example, and you kind of get where I'm going with this, does this give you a proper distribution inside the triangle? Px0, Py0, P, and the XOR measurement all equal to 0. Does this work? And why not? Okay, so piggybacking off of that, we have this sort of proposition that using edge coordinates guarantees that the following are satisfied: non-signaling and normalization. So normalization is kind of straightforward to see because we actually use normalization in the derivation, right about here. So we used normalization in the derivation. And in fact, if you just look at these expressions, you'll see that it's normalized. Why? Because every coordinate comes with 2 pluses and 2 minuses. So when I sum up all of these, all of the P all the p's will cancel out, this one and this one with this one and this one, say. But what you're left over with is -1, +1, +1, +1. That's a total of 2. But then you're dividing by a half. There you go. It's normalized. And also, it will satisfy non-signaling. So we check this one and then non-signaling. This one will be easier to demonstrate by example. So say that I have a set of edge probabilities that are given as follows: 1/4, 3/4, 1, 1/2, and in the middle I have 1/2. Now I'm going to use that formula. So I mean, you can do it. I'm not going to go through all the details. You can use that formula to precisely get all of the probabilities. So P00 is 1/4, P01 is 0, P10 is 1/2, and P11 is 1/4. And you can see that it matches up with the marginals. You have 1/4, 3/4, and 1/2, so on and so forth. And you can also do the same thing with the bottom distribution down here. And you can see that we have that 1/4 plus 1/4 equals 0 plus 1/2. So you can just sort of get the idea by this example. When you use the edge coordinates, you're automatically satisfying non-signaling. The only thing that you need to check when you're using the edge coordinates is that you don't have negativity appearing, because so you still have to require that whatever you have in this formula, that this is greater than or equal to 0. So there's a slightly easier representation of these edge coordinates using the idea of expectation values. So the basic idea is that before we had Alice and Bob have outcomes in 0 or 1. So we want to map to a scenario where just Alice and Bob relabel their outcomes as +1 or -1. To put it simply, we just map whenever Alice or Bob get 0, it gets mapped to +1, and whenever Alice or Bob get 1, it gets mapped to -1, or just -1 to the A. Now, the expectation value is like kind of, in some sense, you could interpret this as like the most likely value that you would observe in a experiment. So you define it quite generally in statistics as the value that you would get times the probability of getting that value. So in our case, it's +1 times the probability of getting +1, which in this case is the same as 0, and -1 times the probability of getting that -1. So rearranging things a little bit, this expected value, which I write inside the brackets, is because this px1 can be written in terms of px0s, I can write this whole thing in terms of this thing is given by a formula for this one, or vice versa. The probabilities are given in terms of the expectations. And so I can do this for either the 0 component or the 1 component, or so I can always use the expectations to get me the probabilities as well. So there's a nice easy mapping between the two. It's just more or less we use this one and this one. But there's a nice sort of one-to-one mapping. I can use without loss of generality the probabilities or the expectations. Notice that while the probabilities will be between 0 and 1, as we expect, the expectations will be between -1 and 1. Why is that? Because I could have that the probability of getting 0 is 1, in which case this value is +1. But if the probability of getting -1 is 1, then this will be 0 and this will be -1. So the range of this thing will be between -1 and +1. So the reason that this is nice is because the probability formula that we wrote above, namely, let's see if I can find it, this one's a little bit difficult to look at, but when you write it in terms of expectations, just by plugging in the formula that we already had, we see that it's sort of more straightforward to look at. You will get Pxy of AB. You take the expectation of Alice, multiply it by the possible outcome that will happen, -1 to the A, the expectation of Bob, -1 to the B, the expectation of Charlie, -1 to the a plus b, which is just the outcomes that they're supposed to get. So this is sort of a more straightforward thing to look at. So, and also the 1 doesn't change signs from +1 to -1 and so forth. So this is sort of a nice formula that we're going to use in our later applications. So just to conclude, with the edge coordinates, we have that normalization and non-signaling are automatically guaranteed, but then you have to enforce, and we will talk about this next time, that these probabilities are greater than or equal to 0. Hope that helps.